Every time we look into deep space, we are looking into the past, because light needs time to cross the distance between worlds. The same is true in the other direction. Earth has been sending its reflected light into space for billions of years, carrying faint traces of every era our planet has lived through. Around 66 million light-years away, that ancient light is only arriving now, so a distant observer could be receiving Earth as it was when dinosaurs still walked here. They would not be seeing our planet as it is today, but a version of Earth that no longer exists. So tonight, the question is simple. Could aliens really be looking at dinosaur-era Earth right now? And what would they actually be able to see? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you could watch Earth from any moment in its past, which era would you choose? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about why aliens could be looking at dinosaurs on Earth right now. Every second, sunlight reaches Earth, reflects from clouds, oceans, ice, deserts, forests, cities, and countless smaller surfaces, then continues outward into space. Most of that light is scattered in directions no human observer will ever follow, and almost all of it becomes weaker as it spreads farther from the planet. But it does not simply vanish when it leaves the solar system. The photons keep moving through the darkness, carrying a faint record of what Earth looked like at the moment they departed. This is easy to forget because light feels almost instantaneous in ordinary life. A lamp turns on, and a room becomes bright without any delay we can notice. Sunlight crosses the distance from the sun to Earth in a little over 8 minutes, which is still short enough that the sun appears to us as though it exists almost in real time. But once the distances become measured in light years rather than kilometers, that tiny delay becomes the central feature of everything we see. A light year is not a measure of time, even though its name sounds like one. It is the distance light travels through vacuum during 1 year, almost 10 trillion kilometers. When astronomers say that a star is 100 light-years away, they are also saying that the light reaching our telescopes tonight began its journey 100 years ago. The star may still be there in much the same state, but what we see is not its present. We see the version of it whose light had enough time to cross the space between us. The same rule applies to Earth in the opposite direction. An observer 1 light-year away would see our planet roughly 1 year in the past. 10 light-years away, the delay grows to around 10 years. A civilization 100 light-years away, if it possessed instruments capable of separating Earth from the sun, could only receive light showing our planet as it existed around a century earlier. The farther the observer is placed, the deeper into Earth's history the arriving light belongs. There is nothing special about the point where a light ray passes the Moon, Pluto, or the outer boundary of the solar system. Once reflected light leaves Earth, it continues outward unless something absorbs or scatters it. Some photons strike dust, gas, planets, stars, or other matter, but enormous numbers continue into interstellar and eventually intergalactic space. They become unbelievably diluted, yet the information they carry about their source is not erased simply because the source is far away. The light leaving Earth is not a perfect movie waiting to be projected somewhere else. What travels outward is a changing pattern of brightness, color, spectrum, polarization, and direction, created by the planet, its atmosphere, its surface, and the star illuminating it. With enough sensitivity, those patterns can reveal remarkable things even when the planet itself is only a tiny point. Humans already use this principle when studying distant worlds. We often cannot see the surface of an exoplanet directly, yet the light associated with that planet can still tell us about its orbit, size, temperature, and sometimes its atmosphere. The challenge becomes much harder with distance. and Earth viewed from millions of light years away would be extraordinarily faint. But the underlying physics remains the same. This means Earth is constantly sending versions of itself into space. Not intentionally, and not as a focused message, but simply because it is illuminated. The blue and white world visible in photographs from the moon is also a source of reflected light spreading outward in every direction. As Earth rotates, cloud systems move, seasons change. Ice grows and retreats, vegetation changes, volcanoes erupt, and oceans reflect sunlight differently. The pattern of escaping light changes with them. There is no single shell carrying one photograph of Earth. Instead, there is a continuous stream, with each moment following the moment before it. Light that left Earth yesterday is now farther away than light leaving today. Light from a century ago is roughly 100 light-years away in the directions where it has traveled without interruption, while light from thousands or millions of years ago has reached vastly larger distances. If we could somehow place ourselves far outside the solar system at different distances, we would not be traveling through Earth's past physically, but we would be standing where older and older light is arriving. At one distance, we might receive photons from the modern world, while farther away we could receive photons that left before electricity, before cities, before agriculture, and eventually before our species existed at all. The idea is useful because it reveals that the past does not disappear from the universe all at once. Information about old events continues traveling outward at light speed long after those events have ended. When a lightning storm passes over an ocean, some of its light can leave Earth and continue after the clouds are gone. When a volcano changes the atmosphere or an asteroid strikes, faint traces of those moments begin journeys that can last far longer than the events themselves. The scale becomes difficult to imagine once geological time enters the story. Human civilization occupies only a tiny portion of Earth's history, while life has been changing the planet for billions of years. Long before there were cities, radio towers, aircraft, or even humans, sunlight was already striking Earth and carrying information away into space. During the age of dinosaurs, the continents were arranged differently. The climate was different. The atmosphere was not identical to today's, and the living world on the surface followed ecosystems that no longer exist. Yet Earth still reflected sunlight. Clouds still moved across the planet. Oceans still scattered blue light, and the atmosphere still left its chemical fingerprints in the radiation escaping towards space. Those photons did not know that the world beneath them would eventually change. They simply left. Some traveled toward nearby stars. Others continued through empty regions of the Milky Way, while Earth changed far behind them. Dinosaurs disappeared. Mammals diversified. Primates evolved. Humans emerged. And civilizations rose, while the oldest of those photons continued outward at the same speed they had always had. This creates a strange relationship between distance and history. When we say that an observer is 1 million light-years away, we are not only describing a huge separation in space, we are also saying that the newest light they can receive from Earth is about 1 million years old. If the observer is 10 million light-years away, then the version of Earth available to them through light belongs to a time long before modern humans. At tens of millions of light-years, the delay reaches deep into the Mesozoic era. The observer is not watching the same Earth we see today from orbit, because the light showing today's planet has only just begun crossing the distance. From their location, the modern Earth is still hidden in the future of the light they have not yet received. That phrase can sound confusing because Earth is not physically existing in two times at once. There is only one Earth at our location, changing from moment to moment, as usual. What differs is the information available at different places. Near Earth, observers can receive very recent light. Farther away, the newest available information is older because it has taken longer to arrive. Every telescope is, in a limited but very real sense, a machine for looking into the past. It does not transport the observer backward in time, and it cannot reveal events whose light has not arrived, but it allows us to receive information from earlier states of distant objects. The farther away the source, the older the view. If an alien astronomer applied the same principle to Earth, our planet would become another delayed object in their sky. They might know the Sun as a distant star and, with sufficiently advanced technology, identify a small planet orbiting it. What they learn about that planet would depend not only on their instruments, but on how far away they are, because distance determines which era of Earth's light is reaching them. An observer close enough to the solar system could, in principle, receive modern Earth light. Farther away, the latest visible version of our planet would move backward through recent history. Beyond the region reached by the light of modern civilization, there would be no optical evidence of today's cities or satellites because those photons have not arrived there yet. Farther still, humanity itself disappears from the available image. The observer is not seeing a future in which humans vanished. They are simply receiving light that left Earth before humans existed. From that perspective, our entire species lies in a part of Earth's story that has not yet reached them. This is where the idea becomes unsettling in a quiet way. Somewhere at the correct distance, Earth can be a living planet while still being completely pre-human in the light available to an observer. A farther civilization could study our world and conclude that it contains life, perhaps even a complex biosphere, while having no evidence that a technological species ever appeared here. If that civilization were tens of millions of light-years away, the delay becomes large enough that the animals dominating Earth's ecosystems would not be anything they would recognize from the modern planet. They would be receiving light from ancient forests, ancient seas, and an atmosphere shaped by a biosphere that existed long before people. The exact details they could recover would depend on technology far beyond anything we possess. At those distances, Earth would be exceptionally difficult to separate from the light of the sun, and individual animals would be far too small to resolve directly. But the photons themselves would still belong to that older Earth, and that is the part that does not depend on imagining impossible telescopes. Every sunrise reflected from ancient oceans, every seasonal change in vegetation, every shift in cloud cover, and every atmospheric signature from those eras contributed faintly to the light spreading away from Earth. Most of it will never be collected by anything, and some may travel through empty space for billions of years without ever striking a detector. Yet the light continues, whether anyone is watching or not. This also means that Earth's history is arranged around us in layers of light. The most recent layers are closest, while older layers are farther away. The farther outward we imagine an observer, the deeper into the planet's past the available photons belong. Modern Earth, industrial Earth, prehistoric Earth, and much older versions of the planet all occupy different expanding distances in the sense of where their light has reached. These are not physical shells with sharp surfaces, because Earth emits and reflects light continuously and in every direction, while the planet, the sun, and the galaxy are all moving. The real geometry is more complicated than a set of perfect spheres. But as a simple way to understand light travel time, the image is useful. Every year that passes, another year of Earth's history moves roughly 1 light-year farther outward. The light carrying evidence of the first cities is still close by, on a galactic scale. The light carrying evidence of Homo sapiens has traveled farther, but still occupies only a small region compared with the size of the universe. The light from the age of dinosaurs has had tens of millions of years to spread into intergalactic space. Earth itself has changed beyond recognition during that same interval. Continents have moved, species have vanished, new species have evolved, climates have shifted, and one group of mammals eventually built instruments capable of asking where the ancient light went. The answer is that it kept going. It crossed distances so large that the Milky Way itself became only the beginning of the journey. Light, from 60 or 70 million years ago, has traveled far beyond our galaxy, passing through a universe filled with other galaxies whose own ancient light is traveling toward us at the same time. And somewhere near the distance that light has reached today, any observer receiving it would not be looking at the Earth beneath our feet now, because the newest version of our planet available there still belongs to an age when dinosaurs walked the world. To understand where that ancient light could be arriving, the easiest place to begin is with the end of the dinosaur age. The non-avian dinosaurs disappeared roughly 66 million years ago, so light that left Earth around that time has now had roughly 66 million years to travel outward. In the directions where it was able to continue freely, that light has crossed about 66 million light-years of space. That distance is far beyond the Milky Way. Our galaxy is only about 100,000 light-years across, so dinosaur-era light left the galaxy behind long ago and continued into intergalactic space. By now, it has reached regions containing other galaxies, galaxy groups, and enormous stretches of nearly empty space, all while Earth itself has changed almost beyond recognition from the world that originally reflected those photons. The number becomes easier to feel when compared with familiar cosmic distances. The Andromeda Galaxy is a little more than 2 million light-years away. Light from Earth during the dinosaur age has traveled tens of millions of light-years farther than that, reaching distances where the Milky Way would appear as only one galaxy among many. An observer around 66 million light-years away, placed in the right direction and able to isolate Earth from the Sun, would therefore receive light corresponding roughly to the period near the end of the dinosaurs. An observer somewhat closer would receive a younger Earth. One farther away would receive an older one. Distance determines which era of Earth's outgoing light is arriving there now. There is no special boundary in space, labeled Dinosaur Earth. The relationship is continuous. At 65 million light-years, the newest arriving Earth light would belong to a somewhat later time. At 70 million light-years, it would come from an earlier part of the Cretaceous. Move farther outward, and the available image belongs to increasingly ancient stages of Earth's history. The light from each moment spread outward in all directions, creating a constantly expanding record around the moving solar system. Reality is more complicated than a set of perfect spheres, because Earth moves around the Sun moves around the Milky Way, and the galaxy itself moves through space. Even so, the central idea remains simple. The farther an observer is from us, the older the Earth light available to them. During 66 million years, the Sun has traveled a significant distance around the center of the Milky Way. So the photons leaving dinosaur Earth were emitted from a region of space that is no longer where the solar system sits today. The ancient light continues along its own path, while its source has moved elsewhere, which makes the geometry more complicated, but does not remove the time delay. If a civilization happened to exist at the correct location and possessed technology capable of detecting our planet, the light entering its instruments would still belong to the Earth that existed when those photons began their journey. The Cretaceous world carried different continents, warmer climates across much of the planet, different coastlines, and ecosystems dominated by organisms that disappeared long before humans appeared. Yet none of those details would automatically appear as a clear picture from 66 million light-years away. The ancient photons carry information from that environment, but carrying information is not the same as making it easy to recover. As light spreads through space, the same radiation is distributed across an ever larger area, making Earth progressively fainter with distance. By the time reflected light from our planet has crossed tens of millions of light-years, Earth would be extraordinarily difficult to detect. The Sun would dominate the system's brightness, while our planet would sit extremely close to it from such a distant point of view. Separating a tiny rocky planet from the glare of its star would be an enormous technical problem even for a civilization far more advanced than ours. That distinction is important, because the main idea does not require us to pretend that aliens could casually watch dinosaurs walking across a field. The light from dinosaur Earth is genuinely out there, and it can genuinely be arriving somewhere now. What remains uncertain is whether anyone exists in the right place, and whether its technology could collect enough of that weak signal to learn anything useful from it. The universe does not guarantee that a civilization is waiting at roughly the correct distance. Most of the space between galaxies is almost completely empty, and even within galaxies, stars occupy only tiny portions of the available volume. An observer would need to exist in a location where Earth's ancient light reaches it, and where the solar system can be identified among an enormous number of other sources. If such observers lived in another galaxy, they would also be seeing the Milky Way in the past. Their view of our entire galaxy would be tens of millions of years old, not just their view of Earth. Our planet would be one tiny world orbiting one ordinary star inside that ancient galactic image. This makes the situation very different from placing an alien telescope just outside the solar system. At 66 million light-years, the observers are not only far from Earth, they are far from our entire galaxy. The light showing dinosaur Earth has crossed intergalactic space before reaching them, arriving in a sky filled with the light of countless other stars and galaxies. Still, there is something remarkable about the fact that the information does not become newer during the journey. A photon that left Earth during the Cretaceous does not update itself as the planet changes. It does not learn that an asteroid struck, that the non-avian dinosaurs disappeared, or that humans eventually built cities. It carries whatever information was present when it left, modified only by whatever happens to it along the way. Newer versions of Earth follow behind. Light from the final days of the dinosaurs moved outward after light from the centuries before them. Light from the first primates came much later. Light from early humans came later still, followed eventually by the faint optical signs of agriculture, cities, industrial civilization, satellites, and the modern planet. Seen this way, Earth's history is moving outward as an enormous sequence. A distant observer does not receive all eras at once. The information arrives in order, separated by the same broad sequence in which events originally happened here. If a civilization around 66 million light-years away began studying Earth today, it might be receiving a planet close to the end of the dinosaur age. If it continued observing for 1,000,000 years, the light arriving over that span would carry the next 1,000,000 years of Earth's old history. The extinction would pass through its observations, followed by the recovery of ecosystems and the changing world that came after. That does not mean the observer would literally see an asteroid strike in cinematic detail. The event might reveal itself only through broad changes in brightness, atmospheric chemistry, dust, or other planetary signals if the instruments were capable enough. The important part is that later events arrive after earlier ones, because the light carrying them left Earth later. For an observer farther away, the extinction has not arrived yet. Their newest Earth light could still belong to a world where non-avian dinosaurs are widespread. For an observer closer than roughly 66 million light-years, that extinction is already part of the past available to them, and the planet they receive belongs to a younger era. This creates a strange map of time across distance. Somewhere, the newest arriving Earth light could belong to the dinosaur age. Elsewhere, it could belong to the rise of mammals. Much closer to us, the available light could belong to human history. Earth itself has only one present, but information from many former versions of the planet occupies different regions of space. If we move farther outward, older Earths appear. Hundreds of millions of light-years away, an observer could receive light from before the dinosaurs existed. At still greater distances, the planet represented by the arriving light would become more unfamiliar as continents, oceans, atmosphere, and life move deeper into geological history. Earth has never been one permanent world moving unchanged through time. It has been a sequence of different versions of the same planet, and light from each version leaves in the same order. The dinosaur example feels especially powerful because those animals are completely lost to our present. Yet some of the light created while they lived is still traveling. If an observer at the right distance could somehow collect enough of it, they would not be looking through a magical portal into the past. They would be doing the same basic thing our telescopes do whenever they study a distant galaxy. The unusual part is simply that the ancient object in their telescope would be our own home. From their point of view, there would be no reason to call that Earth ancient unless they understood what happened later. They receive the light now, and that is the version of Earth currently available to observation. Modern humanity is not hidden from them by weak magnification alone. The light showing modern humanity has not reached them yet. Even a perfect telescope cannot solve that problem. Better instruments can collect fainter light that has already arrived, but they cannot reveal photons that are still traveling through the space between source and observer. This is not an engineering limitation. It is a consequence of the finite speed of light. So a civilization receiving dinosaur-era Earth would be trapped inside that old view until newer light arrived. It could improve its resolution, measure spectra more precisely, and collect more photons. But it could not skip forward to modern Earth. The waiting time would be measured not in years or centuries, but in tens of millions of years. For us, the situation is reversed whenever we look far into space. A distant planet may appear lifeless, even if life has since evolved there. A galaxy may appear young, even though enormous spans of local time have passed since its light began traveling toward us. The universe we see is always assembled from different moments. The dinosaur Earth, moving through intergalactic space, is therefore not an exception to astronomy. It is one of the clearest ways to feel how astronomy always works. We know exactly how dramatically our planet changed after that light escaped, which makes the delay more personal than when we look at an unfamiliar star. Somewhere around the appropriate distance, the light arriving from the solar system can genuinely belong to an Earth inhabited by dinosaurs. Even though the Earth beneath us has already moved through roughly 66 million years of history, the old world is gone from our present, but information from it is still crossing the universe. And yet, receiving that ancient light is very different from seeing a dinosaur clearly, because at tens of millions of light years, Earth would be so small, faint, and buried in the glare of the sun, that the real challenge is not whether the past is arriving, but whether anyone could extract enough detail from it to know what was living here. The difference between receiving light and forming an image from it is enormous. Every telescope works by collecting photons, but useful detail depends on how many photons arrive and how finely the instrument can separate one part of the target from another. Earth is already a small object when viewed from the outer solar system. From another star, it becomes a tiny point. From tens of millions of light years away, the idea of a normal photograph begins to break down almost completely. The first problem is brightness. Earth does not shine strongly in visible light on its own. It reflects a small fraction of the sunlight that reaches it. For an Earth-like planet around a sun-like star, the planet can be around 10 billion times dimmer than the star in visible light. Even for nearby exoplanets, separating that faint planetary signal from the glare of the host star is one of the hardest problems in astronomy. At roughly 66 million light-years, the difficulty becomes extreme. From so far away, the solar system would occupy an unbelievably tiny angle in the sky. Earth and the Sun are separated by a distance that feels enormous to us. But across intergalactic space, that gap becomes so small in apparent angle that distinguishing the planet from the star would be an extraordinary technical challenge before anyone even tried to see. Details on the surface. This is why the familiar science fiction image of an alien telescope zooming in until a Tyrannosaurus Rex fills the screen is misleading. Magnification cannot create detail that was never resolved in the incoming light. An observer can enlarge a tiny blurry point until it fills a display. But if the original measurement contained no separate information about the animal, the enlarged image still contains no animal. Resolution depends on both the wavelength of light and the effective size of the telescope. Larger observing systems can distinguish smaller angular details, and a sufficiently advanced civilization might build enormous arrays of telescopes spread across huge distances, combining their measurements into something like one gigantic instrument. Even then, resolving an individual creature on a planet tens of millions of light-years away would demand a scale of precision far beyond anything humanity has built or seriously planned. The number of arriving photons creates another limit. Earth's reflected light spreads outward in every direction, so only a tiny fraction of it would ever enter a distant detector. As the distance grows, the light becomes more diluted. A civilization could point an enormous instrument directly at the solar system and still receive only a vanishingly small part of the light that left Earth during any short moment in the Cretaceous. Long exposures can collect more photons, but that creates a new problem if the goal is to watch movement. A telescope can gather faint light for hours, days, or much longer, and combine it into one measurement, yet doing that averages rapid changes together. A dinosaur walking through a forest does not remain in the same place while the detector slowly collects enough light. To watch an animal moving, the observer would need both incredible spatial resolution and enough photons arriving quickly enough to make many separate images. That combination is far harder than merely detecting the planet. Finding a faint point of light can be possible even when no surface details are resolved. Measuring a planet's orbit requires more information. Distinguishing continents demands far more, and resolving a single animal would require another enormous increase in detail. Distance does not make all of these tasks equally difficult. Every additional level of detail becomes dramatically more demanding. Earth's atmosphere would complicate the view as well. Clouds cover large parts of the planet at any moment. The world rotates, and only the day side reflects strong visible sunlight. Even a perfect instrument, looking from one fixed direction, could not see every part of the surface at once. A dinosaur could be standing beneath cloud cover, in darkness, or in a forest where its own reflected light is completely overwhelmed by the surrounding landscape. On the scale of the whole planet, even a very large animal is almost nothing. Forests, deserts, oceans, snow, clouds, and continents cover areas vastly larger than any creature. Millions of animals could inhabit the surface while changing Earth's total reflected light, far less than a broad weather system or a shift in cloud cover. The planet could be full of life without any individual organism making a directly visible mark from intergalactic distance. So, if aliens really were receiving Cretaceous Earth light today, the most realistic version of looking at dinosaurs would be much quieter. They might be looking at light from a planet where dinosaurs are alive, while never resolving a single dinosaur. Their instruments could tell them that a rocky world exists beside the sun, perhaps measure its orbit, and perhaps begin learning what kind of environment it has, while the creatures on its surface remain completely invisible. That does not mean the unresolved point would be empty of information. A planet changes brightness as it rotates because different surfaces reflect different amounts of light. Oceans, clouds, ice, deserts, and vegetation do not behave identically, so the integrated signal from Earth changes as different regions rotate into view. With sufficiently precise measurements, an observer could detect patterns without ever forming a map. The rotation itself could leave a repeated rhythm. If broad regions of land, ocean, and clouds affect the planet's brightness in recognizable ways, the observer might detect a cycle close to the length of an Earth day. They would not watch a continent move across a screen, but they could infer that the world is turning and that its surface is not uniform. Longer observations could reveal seasonal changes as well. The angle of sunlight shifts through the year, weather patterns change, vegetation responds to climate, and ice can expand or retreat. On Dinosaur Earth, the exact patterns would differ from those of the modern planet. But the basic idea remains. A world that cannot be resolved into a detailed image can still reveal itself through the way its light changes over time. This is closer to how much of astronomy already works. Stars are usually points even in powerful telescopes, yet their light tells us about temperature, chemical composition, motion, and other properties. We learn by measuring spectra, brightness, and timing, rather than by seeing a detailed surface. A distant planet could be studied in the same way. If an alien civilization managed to isolate Earth's light from the sun, it could potentially measure the planet's orbit and estimate how much energy it receives from its star. Repeated observations might reveal rotation, changing clouds, or large differences between surface regions. Thermal measurements could provide information about temperature. None of this requires an image sharp enough to show an animal. The atmosphere could be even more valuable. Gases absorb and emit light at particular wavelengths, leaving patterns in a spectrum. If enough planetary light could be separated from the star, those patterns could reveal some of the gases surrounding Earth. A planet may remain a single unresolved point, while its atmosphere still leaves a detectable chemical signature. That is why future human searches for life around other stars are expected to rely heavily on spectroscopy. We may not see forests, oceans, or creatures directly, but we can search for combinations of atmospheric gases that suggest unusual chemistry. The goal is not to take a photograph of an alien animal. It is to ask whether the planet's environment shows signs that are difficult to explain without biological activity. Cretaceous Earth would have been an interesting target for that kind of observation. It was a world with oceans, clouds, active geology, and a huge biosphere. Its atmosphere was not identical to today's, but life had already been altering Earth for an immense span of time. A sufficiently advanced observer might therefore detect a planet that looks chemically active long before understanding what kinds of organisms are responsible. The strongest clues would likely come from combinations rather than one single gas. Oxygen can be associated with biology, but under some conditions, non-living processes can also produce it. Methane can come from organisms or geology. Water is important for life as we know it, but water alone does not prove anything is alive. A convincing interpretation would require understanding the star, the planet, the atmosphere, and the processes that could maintain the observed chemistry. An alien civilization could therefore spend years studying Dinosaur Earth and still remain uncertain. They might see a rocky planet at a promising temperature, detect water vapor, identify chemically interesting gases, and measure changes that suggest a complex surface. The evidence could grow stronger without ever becoming a direct image of life. They might eventually conclude that the planet has a biosphere while knowing almost nothing about its appearance. They would not know that giant reptiles walk across continents, that birds exist, or that mammals are present in smaller ecological roles. A living world can reveal itself on a planetary scale without revealing the shape of the organisms doing the living. The sun would remain the greatest obstacle, blocking or suppressing its light with enough precision to isolate Earth would be difficult even if the planet were nearby. At tens of millions of light-years, the required sensitivity and angular resolution become almost unimaginable. Nothing guarantees that even a very advanced civilization could overcome every part of that problem. But the title does not require them to possess a magical telescope. It only requires that dinosaur-era light is reaching some distant region now, which follows directly from light travel time. Whether anyone can detect Earth inside that light is a separate question, and whether they can recognize life is another question beyond that. If the observer were closer, The task would become easier, because Earth would be brighter and more widely separated from the Sun, in angular terms. But the light arriving there would belong to a much younger Earth. To receive the dinosaur era today, the observer must be tens of millions of light years away, and that very distance is what makes the planet so difficult to study. A civilization with extraordinary technology might solve part of this by using many telescopes working together. Enormous collecting areas, advanced starlight suppression, and years of repeated measurements. Instead of seeing one perfect image, it could slowly build a statistical portrait of the planet from small changes in light. That portrait might reveal a rotating world with changing clouds, large bodies of liquid, a complex atmosphere, and chemical conditions that appear difficult to maintain without continuous processes on the surface. Each clue would narrow the possibilities while still leaving the actual creatures hidden. The dinosaurs themselves would remain almost completely beyond reach. Their bodies are too small, their movements too local, and their reflected light too insignificant compared with the whole planet. Even the largest animals that ever walked on land would disappear into the total brightness of continents, oceans, and atmosphere when viewed from such a distance. Yet life does not have to be visible as a body to alter a planet. Organisms can transform gases, surface colors, seasonal patterns, and chemical cycles on scales much larger than themselves. Over enough time, biology can leave fingerprints that spread across an atmosphere or an entire world. That means an alien astronomer might never see a dinosaur and still discover something far more important: that the ancient Earth is not merely a wet rock orbiting an ordinary star. It is a planet whose environment appears to be continuously shaped by living processes. And if the surface itself could never be resolved clearly enough to reveal an animal, the atmosphere surrounding dinosaur Earth might still carry the larger clues an advanced observer would search for, raising the deeper question of whether they could recognize our planet as a living world without ever seeing what lived on it. A distant civilization would not need to identify a forest, an ocean, or a single creature to begin answering that question. A planet's atmosphere interacts with light in ways that reveal its composition, because different gases absorb particular wavelengths more strongly than others. If enough light can be collected and separated into a spectrum, those patterns become chemical fingerprints. For Earth, some of the most interesting molecules would include water vapor, carbon dioxide, oxygen, ozone, and methane. None of them is a photograph of life, and none is perfect proof on its own. But together, they can describe a planet whose atmosphere is active, chemically complex, and potentially habitable. The more completely an observer understands the star, the planet, and the surrounding environment, the more meaningful those measurements become. Water would immediately make the planet more interesting, because liquid water is central to life as we know it. Yet water alone would prove nothing. Many lifeless worlds can contain water in some form. Carbon dioxide would help describe climate and atmospheric structure, but it would not establish biology either. Venus and Mars both show how familiar molecules can exist on worlds that do not resemble the living Earth. Oxygen would be more provocative. On modern Earth, the large amount of oxygen in the atmosphere is closely connected to photosynthetic life, which continually replenishes a gas that readily reacts with other materials. An observer measuring abundant oxygen might therefore suspect that some active process is maintaining it. But oxygen is not an automatic sign of biology. Under certain conditions, non-living chemistry can also produce significant oxygen, especially when radiation breaks apart molecules and the planet lacks sufficient ways to remove the resulting gas. A careful civilization would need to understand the sun's radiation, Earth's water inventory, atmospheric escape, and surface chemistry before deciding what the oxygen meant. Methane would add another clue, because it can be produced biologically and geologically, and it does not remain indefinitely in an oxygen-rich atmosphere. Finding several gases together especially ones that should react away without continual sources, could make a lifeless explanation harder to maintain. The important idea is that the aliens would not be searching for one magical molecule labeled life. They would be searching for a combination of clues that seems chemically difficult to maintain without continuous activity. A living planet can push its atmosphere away from simple equilibrium. But geology, radiation, oceans, and atmospheric loss can also create surprising chemistry. Context would matter as much as detection. This kind of investigation would be slow. The alien astronomers might spend years refining models of the Sun, Earth's orbit, the planet's temperature, its likely atmospheric pressure, and the reactions occurring in the atmosphere and surface. Every new measurement could eliminate some explanations while strengthening others. A convincing case for life would emerge through accumulation rather than one dramatic observation. Dinosaur Earth would be an especially interesting target because it was already a mature biological world. Life had been altering the planet for billions of years before the late Cretaceous. Photosynthetic organisms were widespread. Oceans contained enormous ecosystems. Vegetation covered large areas of land, and Earth's atmosphere was deeply connected to biological activity. The atmosphere was not identical to the one we breathe today, and that matters. Carbon dioxide, climate, vegetation, continental arrangement, and other conditions changed throughout the Cretaceous. A distant observer would not be studying some timeless model of Earth. It would be receiving one specific stage of a planet that has always been changing. Those changes could themselves provide information. If the observatory were sensitive enough to measure Earth through many rotations and orbits, the signal might vary as clouds moved, seasons shifted, vegetation changed, and different parts of the planet turned toward the observer. The world could remain unresolved while still showing patterns that repeat over hours, months, and years. A repeated daily rhythm could suggest rotation. A slower annual cycle could reveal seasons. Different surfaces reflect light differently, so a changing mixture of ocean, land, cloud, ice, and vegetation could alter the planet's brightness and color as it turns. The observers would not see a continent as a shape, but they could infer that the surface is not uniform. The atmosphere could be more useful because it represents the planet on a global scale. A forest may disappear beneath clouds, but gases, such as oxygen, ozone, carbon dioxide, and water vapor, are distributed through huge volumes of air. That makes atmospheric spectroscopy one of the strongest tools for learning about a world that cannot be resolved into a detailed image. The aliens might also observe Earth in infrared wavelengths, where the planet emits heat. That could give clues about temperature and about how heat changes as the planet moves around the Sun. A world with temperatures compatible with liquid water, persistent weather, an active atmosphere, and chemically unusual gases would become increasingly difficult to dismiss as an ordinary barren rock. Clouds would complicate the observations, while also revealing that the atmosphere is dynamic. Their constant movement could hide the surface and add noise to brightness measurements, but persistent weather would itself be meaningful. This is not a static, airless body. It is a planet where heat and water are being moved around continuously. After years of measurements, the evidence might begin to form a coherent portrait. Earth rotates rapidly, has a substantial atmosphere, contains water, experiences weather, and occupies a temperature range where liquid water can exist. Its atmosphere contains gases that demand explanation, and its reflected light changes in ways consistent with a complex surface. At that point, the problem becomes whether non-living processes can reproduce the entire picture at once. False positives are important because almost every individual clue has another explanation. Oxygen can sometimes accumulate without life. Methane can be produced geologically. Water is common in many environments. Organic molecules can form through non-biological chemistry. A strong claim of life requires several independent observations that point in the same direction, while alternative explanations become increasingly strained. The Sun would need to be understood as carefully as the planet, because stellar radiation affects atmospheric chemistry. The planet's size and mass would matter too, since gravity affects atmospheric escape and surface pressure influences climate. Oceans, volcanism, and rock chemistry can create or remove atmospheric compounds. Life cannot be interpreted separately from the physical world it inhabits. This makes the realistic version of alien observation less dramatic but more powerful. Instead of one impossible close-up of a dinosaur, the scientists would build a model of an entire planet from faint light. They might estimate its day, year, temperature, atmosphere, clouds, surface diversity, and chemical cycles, while never seeing more than a point beside the Sun. Eventually, they could become confident that Earth is inhabited while knowing almost nothing about what the inhabitants look like. The conclusion might be that the planet contains persistent chemical imbalance, abundant water appears possible, atmospheric and surface changes repeat through time, and the simplest overall explanation involves a large biosphere. That conclusion would immediately create a much larger unknown. Is the life microscopic or complex? Does it exist only in the oceans? Has it spread across the continents? Are there forests, animals, or anything capable of intelligence? The same planetary clues that suggest life reveal almost nothing about biological diversity. The gap between knowing a world is alive and knowing what lives there could remain enormous. Even an advanced observatory might correctly classify dinosaur Earth as inhabited, while being unable to tell whether its largest organisms are the size of insects or buildings. Planetary scale measurements average away the details that make an ecosystem recognizable to us. The aliens might therefore build scientific models of Cretaceous Earth that are accurate in broad terms and wrong in nearly every biological detail. They could infer oceans, weather, atmospheric oxygen, a stable climate, and a powerful biosphere, while imagining organisms unlike anything that actually existed. That is not so different from the problem humans may face if we someday find a strong biosignature around another star. We could know that something is maintaining unusual chemistry in a distant atmosphere, while having no idea whether the cause resembles bacteria, forests, floating colonies, or life with no close Earth equivalent. For the distant observers studying us, there would be another complication they could not recognize immediately. The biosphere they are detecting is already gone in its Cretaceous form. The measurements arriving in their instruments describe a living world, but that world has continued changing for roughly 66 million years while the light traveled. Many species influencing that ancient environment vanished. New ecosystems replaced them. Mammals expanded into different roles. Primates appeared much later, and eventually one species began altering the planet through technology. None of this has reached the distant observers yet. Their atmospheric spectrum can therefore be perfectly measured, and their conclusion that Earth is alive can be completely correct, while almost everything they assume about the planet's current condition is tens of millions of years out of date. This is where distance becomes more than a technical obstacle. It separates observation from reality in time. Even the best analysis can only describe photons that have already arrived. The telescope may be extraordinary, the chemistry may be understood, and the model may be accurate, but Earth itself has already moved far beyond the era being studied. If the observers continued watching, the signal would slowly change as later chapters of Earth's history reached them. The end Cretaceous extinction would eventually enter their data. Climate and atmospheric conditions would shift, ecosystems would recover, and the biosphere would continue shaping the planet under a different collection of species. Millions of years later, in their own future, another biological Earth would arrive. Later still, another one, The planet would never appear as a permanent, unchanging object, because Earth's atmosphere, surface, and life have always evolved together. This means the ability to recognize life depends partly on which Earth an observer happens to receive. Our planet has not always carried the same atmospheric biosignatures. For long stretches of its history, life existed while oxygen was far less abundant than it is today. Other eras would present different gases, different surface colors, and different levels of detectability. An alien civilization looking at one era might find strong evidence for a biosphere, while another civilization farther away could receive a much older Earth, whose life is harder to recognize remotely. Both would be observing the same planet, but the available light would describe different stages of its evolution. The dinosaur Earth is therefore only one slice through a much larger pattern. Around us, light from many former Earths is still traveling outward, worlds with different continents, different atmospheres, different climates, and different dominant forms of life. The farther away an observer is, the earlier the version that arrives. Somewhere, Earth's light may describe a world dominated by dinosaurs. Somewhere closer, it describes later mammal ecosystems. Closer still, it begins to contain humans, agriculture, cities, and eventually technology. And once we realize that a distant observer might recognize dinosaur Earth as alive without ever seeing a dinosaur, the stranger idea begins to appear. There is no single version of Earth being shown to the universe, because different distances are receiving completely different chapters of our planet's history. The easiest way to picture this is to stop thinking of Earth as sending one image outward, and instead think of it as producing a continuous stream of changing light. Every hour, every season, every century, and every geological era adds another layer to that stream. The planet changes, the reflected sunlight changes with it, and newer information follows older information into space at the same universal speed. An observer 10 light-years away receives a very recent Earth compared with cosmic history. An observer 1,000 light-years away receives a planet from roughly 1,000 years earlier. At 1,000,000 light-years, the available light belongs to a world before modern humans existed. At tens of millions of light-years, the signal reaches back toward the age of dinosaurs. The farther the observer is from the solar system, the earlier the version of Earth that can possibly have reached them. This does not create many physical Earths. There is only one planet here, moving through its own history as usual. What exists at different distances is delayed information. Two civilizations at different distances could study the same planet at the same moment and receive descriptions of completely different worlds. One civilization might detect a modern blue planet with industrial activity. Another, farther away, could receive an Earth where agriculture has not yet begun. Farther still, humans disappear entirely from the available light. At much greater distances, mammals are no longer dominant, and the planet becomes a Cretaceous world with different continents, different climates, and ecosystems filled with animals that vanished long before anyone could build a telescope. The effect continues through every stage of Earth's history. Light from the final days of the dinosaurs moved outward, followed much later by light from the rise of mammals, the evolution of primates, the appearance of Homo sapiens, the growth of cities, and eventually the modern technological world. Each era follows the one before it, separated by the same broad intervals that once passed here. If observers were placed at many distances from the solar system, each could be receiving a different chapter today. The closer observers would have access to newer information, while those farther away would remain deeper in our past. There would be no single universal picture of Earth shared by all of them. Across stellar distances, every observation is delayed. Across intergalactic distances, the delay becomes geological. A planet can evolve whole ecosystems, while its older image is still crossing space. A species can appear, dominate the surface, and disappear before another observer receives the light showing that species at all. Somewhere closer than the dinosaur light distance, observers could receive Earth during the expansion of mammals. Closer still, they might receive the planet during the evolution of early hominins. At much smaller distances, the newest information could belong to a world where humans exist, but modern civilization does not. An observer a few thousand light-years away might receive a human Earth with agriculture and cities, but without electricity, satellites, or radio. The exact historical period depends on the distance. Yet the broader point is simple. Intelligent organisms can exist on a planet long before that planet becomes technologically obvious. Closer again, within hundreds of light-years, the arriving light begins to approach the modern industrial era. Large changes to land, atmospheric pollution, artificial lighting, and other technological effects could eventually become parts of the signal, though detecting them remotely would still be extremely difficult. Distance, therefore, determines two things at once. It makes Earth fainter, and it selects which era is available to study. A nearby civilization gets a brighter, more recent target. A distant civilization gets an older Earth, but faces a much harder observational problem. That creates a strange trade. To see deep into Earth's past, an observer must be far away. But moving farther away also makes the planet harder to detect and separate from the Sun. The most ancient versions of Earth are also the versions that are most difficult to study. A civilization receiving a recent Earth from 50 light-years away would have an easier target than one receiving dinosaur Earth from tens of millions of light-years away. Earth would appear much brighter and more widely separated from the Sun in angular terms. But the easier view would come with newer information. There is no single location from which the whole story can be watched at once. An observer cannot sit at one distance and see dinosaur Earth, medieval Earth, and modern Earth simultaneously. Those moments arrive, one after another, separated by the same time that originally passed between them. If a civilization roughly 66 million light-years away began observing Earth today, it could in principle receive light from near the end of the dinosaur age. If it continued watching for 100 years, it would receive roughly the next 100 years of that ancient history. It would not jump forward to humans simply because its telescope improved. To reach the modern era in its observations, it would have to wait on the order of 66 million more years. Better instruments could improve the quality of the light already arriving, but they could not bring later centuries forward. The sequence is fixed by the speed at which information crosses the distance. A civilization could therefore discover a living dinosaur-era Earth and build an entire scientific tradition around a world that, from our point of view, no longer exists. Generations of alien astronomers might study its climate and atmosphere, while the real Earth has already changed for tens of millions of years. Their conclusions could be excellent and still describe ancient history. They might correctly determine that Earth has oceans, weather, a biosphere, and a chemically active atmosphere, while remaining completely unaware that the dominant animals of that world eventually vanished. The same problem would apply to us if we found a living planet very far away. A strong biosignature could tell us that life existed when the light left, but it could not guarantee that the same biosphere exists now. The farther the world is, the larger the interval during which it may have changed. The dinosaur example pushes this to an extreme. Somewhere far enough away, the most recent Earth available to observation may still be one where no human has ever lived. The observers are not missing us because their telescope is weak. The photons showing us have simply not arrived. Modern Earth follows behind the dinosaur light by roughly 66 million years of travel. The photons leaving our planet tonight are only beginning that enormous journey. Long after today's cities have changed or vanished, those photons will still be moving outward. This creates a strange sense in which the universe contains delayed records of Earth at many ages. The records are incomplete, faint, scattered, and probably never collected in most places, but the information continues traveling. The past is not stored in one location. It is carried outward by radiation. So even the detectability of life has a history. There may have been eras when Earth was alive but looked ambiguous from far away, followed by eras when atmospheric chemistry and surface changes made biological activity easier to suspect. The planet's ability to advertise life changed as life itself changed. Technology is different because it occupies only a tiny fraction of that timeline. Cities, industrial gases, satellites, artificial lighting, and powerful transmitters are extremely recent compared with the biosphere. A distant observer can receive a version of Earth rich with complex life, while having no evidence that technological intelligence ever developed here. For most of Earth's history, that would be the correct impression. Complex animals existed for hundreds of millions of years before radio transmitters appeared. Dinosaurs dominated land ecosystems for an enormous span of time without producing anything resembling the signals of modern civilization. Even after humans appeared, Earth remained technologically quiet for almost all of our existence. A civilization several thousand light-years away could receive light from a human Earth and still see no sign of electricity, radio, satellites, or industry. Intelligence does not automatically make a planet technologically visible. Only very recently did Earth begin adding a different kind of outward signal. Instead of merely reflecting sunlight and emitting natural radiation, humans started producing radio transmissions, radar, television signals, and communication beams, some of which escape into space. Compared with the ancient optical light of Earth, those signals are newborn. Dinosaur-era reflected light has had tens of millions of years to travel. Human radio leakage has had only about a century to spread beyond the solar system, depending on which transmissions are counted. On a cosmic map, the difference is enormous. Natural light from Earth has been traveling outward for billions of years, while strong technological emissions occupy only a small region around the Sun. The evidence that Earth has a biosphere has had vastly more time to spread than the evidence that one species built transmitters. That means a distant observer could know that Earth is alive long before it has any reason to suspect intelligence. A civilization tens of millions of light-years away might study a rich Cretaceous biosphere, while every sign of radio, satellites, cities, and industry remains tens of millions of years from reaching it. Even many hypothetical observers inside the Milky Way would still be receiving a pre-technological Earth. If they are more than roughly a century of light travel time away, humanity's earliest radio emissions have not yet reached them. They might receive optical light from the 19th century or earlier, while the technological signal remains on the way. This makes the contrast with dinosaur Earth even sharper. The ancient planet has been sending natural light through intergalactic space for tens of millions of years, while humanity's technological presence has barely begun spreading through the local stellar neighborhood. The more distant the observer, the older and less technological our planet becomes. Move far enough away, and cities vanish. Farther still, humans vanish. Keep going, and mammals lose their dominance, until the arriving light belongs to a world where dinosaurs still shape the land. This is not because the past still exists physically somewhere beyond us. It is because information from the past has not finished traveling. Every observer is limited to the light that has reached them, and no telescope can reveal a newer Earth before newer photons arrive. The result is a universe in which different civilizations could hold completely different but equally accurate pictures of the same planet. One could know a technological Earth, another a human but pre-industrial Earth, another a world of early mammals, and another a dinosaur planet. Each would be correct about the light in front of them, and wrong if they assumed that light described Earth's present. Seen from our side, the same warning applies whenever we study distant worlds. The farther away a possible living planet is, the more careful we must be about using the word now. We may be detecting life that no longer exists, or seeing an apparently empty planet whose future has already become biologically rich. Earth offers a perfect demonstration, because we already know the later chapters. We know what happened after the dinosaurs. A distant observer receiving their era does not, and the missing future is not hidden in the data. It is still physically on its way. And once Earth's history is viewed this way, the next difference becomes impossible to ignore, because the planet has been sending natural light into space for billions of years, while the technological signals that could reveal modern humanity have traveled only a tiny fraction of that distance. For almost the entire history of Earth, there was nothing in the planet's outgoing radiation that clearly announced the presence of a technological civilization. Sunlight reflected from oceans and clouds, heat escaped into space, lightning produced radio waves, and the atmosphere carried the chemical effects of biology. But none of those things required cities, machines, or intelligence. A distant observer might have suspected that Earth was alive long before there was any reason to suspect that one species had learned to build transmitters. That changed only recently. During the last little more than a century, humans began producing artificial radio signals powerful enough for some of their energy to escape beyond the atmosphere and continue into space. Radio broadcasting, television, radar, spacecraft communications, and other technologies added patterns to Earth's electromagnetic output that natural processes do not produce in quite the same way. Compared with the age of the planet, this technological period is almost invisible. Earth is more than 4.5 billion years old. Complex animals have existed for hundreds of millions of years, and dinosaurs dominated land ecosystems for an immense span of time. Human radio technology occupies only a thin line at the end of that history. The difference becomes even more dramatic when translated into distance. A signal traveling at the speed of light for 100 years can reach a point roughly 100 light-years away. That sounds enormous by human standards, and it includes many nearby stars, but the Milky Way is about 100,000 light-years across. Even the oldest human-made radio emissions have therefore crossed only a tiny part of our galaxy. The word bubble is often used to describe this expanding region, as if Earth were surrounded by a sphere containing all of our broadcasts. It is a useful picture, but reality is less simple. Different signals began at different times, were transmitted at different frequencies and powers, and were aimed in different directions. Some spread broadly, while others were tightly focused. The result is not a perfectly uniform shell of equally detectable human noise. There is another important distinction between a signal reaching a location and being detectable there. Radio waves spread and weaken as they travel, just as reflected light from Earth becomes fainter with distance. A century-old broadcast may have physically passed through a nearby star system while being far too weak to stand out against natural radio noise, with the instruments available there. To detect us, a distant civilization would need to be listening at the right time, in the right part of the spectrum, with instruments sensitive enough to distinguish an artificial pattern from everything else in the sky. If the transmission were highly directional, the observer would also need to be positioned close to the beam. Technological detectability depends not only on distance, but on how a civilization uses energy and what another civilization chooses to search for. Still, the age limit cannot be avoided. No observer more than roughly a century of light travel time away can have received humanity's earliest radio-era signals yet, regardless of how powerful its telescope might be. The information simply has not had enough time to travel farther. That creates an extraordinary contrast with the dinosaur Earth discussed earlier. An observer, tens of millions of light-years away, could be receiving light from a planet covered in complex life, while the first radio signals made by humans remain tens of millions of years away from reaching the same location. To those observers, technology has not merely gone undetected. In the information available to them, it has not happened yet. Their Earth could contain vast forests, moving continents, changing climates, oceans full of life, and animals spread across every major environment. Its atmosphere might carry strong biological clues. Yet, there would be no radar, no artificial satellites, no communication networks, and no industrial civilization in the light reaching them. This reveals how different biosignatures and technosignatures can be in time. A biosphere may alter a planet for billions of years. A technological civilization might produce detectable signals for a much shorter period, perhaps centuries, thousands of years, or something longer if it survives and continues using technologies visible from afar. We have only our own brief example, so we do not know what a typical technological lifetime would look like. NASA uses the term technosignature for observable evidence of technology, and radio is only one possibility. Narrowband radio signals, pulsed lasers, artificial atmospheric chemicals, unusual structures, or other large-scale effects could, in principle, reveal a civilization. The important feature is that the signal is difficult to explain through ordinary, non-technological processes. From another star, however, most human technosignatures would be difficult to detect with technology like ours. Earth remains a small planet beside a bright sun, and many human activities affect only a tiny fraction of the planet's total light. A civilization similar to ours might therefore be much harder to notice than science fiction often suggests. A deliberate beacon would be different. If humanity chose a nearby star and transmitted a powerful narrowband signal directly toward it for a long time, that signal could be much easier to detect than ordinary leakage. Concentrating energy into a narrow frequency and direction allows the signal to stand out more clearly from natural sources. But all of that belongs to Earth's future light. Observers farther away must wait for it. This is where the finite speed of light becomes almost unforgiving. Suppose humanity transforms the solar system over the next 1,000 years and creates unmistakable technological signs around several planets. A civilization 10,000 light-years away cannot know about those changes until the relevant light and signals have crossed those 10,000 light-years. Until then, its view of the solar system remains older. At the scale of the dinosaur example, the mismatch becomes almost impossible to bridge. A civilization 66 million light-years away could study Earth near the end of the Cretaceous and perhaps become convinced that the planet has life. If they are observing that light today, they still have no access to the light of modern humanity because that light remains roughly 66 million years away from their location. If they discovered a strong biosignature and chose to keep watching, their observatories would receive Earth's history at the same pace it originally unfolded. 1,000 years of their observations would reveal roughly 1,000 more years of ancient Earth, not millions. The arrival of humanity would remain almost unimaginably distant. That creates a different version of the problem of contact. Two technological civilizations do not merely need to exist somewhere in the universe. Their detectable periods must overlap in a way that allows signals from one to reach the other while the other is still capable of receiving and responding. Earth's radio waves already have this property. If a signal transmitted decades ago eventually reaches a distant receiver, the receiver learns something about the Earth that existed when the signal left. Any reply begins a new journey, and by the time it returns, both worlds have continued changing. At a distance of 10 light-years, a simple exchange takes at least 20 years for a message to go out and a reply to come back. At 100 light-years, the minimum round trip becomes 2 centuries. Across 1,000 light-years, conversation stretches across 2,000 years. Across tens of millions of light-years, the word conversation stops fitting ordinary human experience. The observers receiving Dinosaur Earth are therefore not potential pen pals waiting just beyond some cosmic delay. If they transmitted a response toward the solar system after detecting our ancient biosphere, Their message would have to cross the same enormous distance that Earth's old light crossed to reach them. By the time such a message arrived here, the difference between the world they observed and the world receiving the reply would be larger than the difference between the dinosaurs and us. The signal would have been sent because of a planet that vanished from its ancient form millions of years before the sender even knew it existed. For nearby civilizations, that delay may still permit meaningful exchange across generations. For intergalactic civilizations, a message can become an archaeological object before it reaches its destination. The sender may be gone, the receiver may be transformed, and the reason for the message may belong to a world that no longer exists. The contrast between natural and technological signals makes this even more striking. Earth's biosphere has had billions of years to leave faint clues in escaping light, but humanity's radio age has barely begun. A distant observer can therefore receive abundant evidence from periods when life flourished while remaining completely outside the region reached by our technology. Seen from 66 million light-years away, there is no contradiction in calling Earth alive and technologically silent. That is exactly what the arriving information would describe. The dinosaurs can belong to the observer's present view, while human radio remains in its future. And if a civilization that far away recognized ancient Earth as a living planet and decided to answer what it saw, the reply would begin another journey measured in tens of millions of years, turning a simple message into something that could reach Earth only after our own civilization had become unimaginably ancient history. Suppose the observers are roughly 66 million light-years away, and the light reaching them today shows Earth near the end of the dinosaur age. They study the tiny planet, become convinced that it is alive, and decide to transmit something toward the solar system. The message leaves immediately from their point of view, but even a perfectly aimed signal traveling at the speed of light would need roughly 66 million years to reach us. That single delay changes the meaning of contact. The aliens would be responding to an Earth that existed about 66 million years before they sent the message, while the Earth receiving their reply would exist about 66 million years after that moment. The message would therefore connect two versions of our planet separated by roughly 132 million years of Earth's history. Nothing about that resembles a normal conversation. There is no question followed by an answer, no exchange that remains inside one lifetime, and no certainty that the civilization on either side survives long enough to know what happened. A transmission sent because dinosaurs were alive could arrive on a world whose continents, climates, ecosystems, and dominant species are completely different from anything the sender observed. If humanity still exists 66 million years from now, it may not resemble the civilization living here today. Languages can become unrecognizable in only thousands of years. Technologies can transform within centuries, and species themselves evolve across millions. On that timescale, even the biological form of whatever receives the message cannot be assumed. Earth would continue changing as well. Tectonic plates would move, mountain ranges would rise and erode, ocean basins would change, and the arrangement of continents could become unfamiliar. The sun would still be shining on such a timescale, but the planet beneath it would have accumulated another geological chapter as long as the entire span separating us from the extinction of the non-avian dinosaurs. A signal arriving then would feel less like mail and more like an artifact from deep time. The information could remain encoded in the electromagnetic wave even if the civilization that produced it disappeared millions of years earlier. Future observers might determine the direction it came from and estimate its distance, yet everything about the sender's current condition would remain hidden behind the same light travel delay. If Earth answered immediately after receiving it, the reply would need another 66 million years to cross back. A simple two-way exchange would therefore require timescales comparable to major episodes in biological evolution. Preserving the meaning of the original message, the language used, the receiving equipment, and the desire to keep listening would require continuity far beyond anything human civilization has experienced. Nothing in known physics prevents information from making that journey. The difficulty lies in the changing worlds at both ends. Societies can rise and fall. Communication methods can change. Habitats can move, species can evolve, and entire civilizations can disappear while the signal continues traveling through nearly empty space. This is where intergalactic communication becomes fundamentally different from communication between nearby stars. 10 light-years creates a delay that can still fit inside a human lifetime. 100 light-years stretches a round trip across generations. Thousands of light-years push an exchange into historical time. Tens of millions of light-years move it into geological time, where sender and receiver belong to different ages of their planets. The distant civilization might still choose to transmit without expecting a response. A message can have value even when there is no realistic conversation waiting at the other end. It could describe their mathematics, biology, star system, history, or simply the fact that they existed. In that form, the transmission becomes a beacon or time capsule, rather than the opening line of a dialogue. Even then, they would be sending into uncertainty. The planet that attracted their attention is alive in the light reaching them, but they cannot know what happened during the 66 million years hidden between that image and Earth's actual present. The biosphere they are addressing may have changed completely before the first bit of their message even begins its return journey. They could be sending a message to a dinosaur world and reaching something else entirely. The same effect appears at smaller distances, only in less extreme form. A civilization 1,000 light-years away might receive Earth from roughly 1,000 years ago. If it responded, its message would arrive roughly 1,000 years from now, connecting the Earth it observed with an Earth separated from that image by about 2,000 years. Distance, therefore, changes more than travel time. It changes what kind of relationship is possible between civilizations. Nearby worlds might exchange information across decades. Distant regions of the Milky Way would communicate across generations. Civilizations in other galaxies could exchange records between eras rather than conversations between contemporaries. This also means that detecting a message from very far away would tell us almost nothing about whether its sender still exists. The signal proves that technology existed when the transmission was made, but the source may have changed completely during the time its information spent crossing space. If humans detected an artificial signal from 1 million light-years away, it would describe a civilization as it was roughly 1 million years ago. The sender could still exist, could have transformed beyond recognition, or could have vanished. No telescope could show us its true present until much newer light had enough time to arrive. A reply from Earth would carry the same uncertainty in reverse. We could answer knowing that our signal would not reach the source for another million years. Whoever eventually receives it might have no cultural memory of the transmission that inspired our response. They could encounter our message as something connected to an event buried in their own deep history. At 66 million light-years, even preserving context becomes extraordinary. Human writing is only thousands of years old, and modern scientific institutions are younger still. A civilization would need to preserve records across a span longer than the history of many animal groups, simply to remember why it once transmitted toward a small planet in another galaxy. The signal itself may survive more easily than the society that created it. Electromagnetic radiation can cross enormous stretches of empty space, but institutions are physical systems living on changing planets. The universe allows a message to keep moving without making any promise that someone will still be waiting when it arrives. If such a transmission were clearly artificial, the discovery would still be enormous. Future scientists might decode numbers, images, maps, or descriptions of the sender's environment. They could reconstruct part of a civilization separated from them by both distance and time, while knowing that every detail might describe a world that no longer exists. A map of cities could show places erased millions of years ago. A description of oceans might refer to coastlines that have shifted beyond recognition. An image of the species that transmitted the signal could represent organisms extinct for longer than humanity has existed. The message could be completely accurate and completely obsolete at the same time. That is one of the deepest consequences of finite light speed. Information can remain meaningful after the source that created it has changed or disappeared. We already see this throughout astronomy. A distant stellar explosion reaches us only after its light completes the journey, and a faraway galaxy is observed in an earlier state rather than as it exists at some inaccessible universal present. A technological signal would obey the same rule. It could arrive carrying the voice of a civilization that vanished before the receiver's ancestors existed. Distance does not destroy the information immediately. It separates the information from the present condition of its source. The dinosaur Earth scenario makes this especially personal, because our own planet becomes the ancient astronomical object. Light from an Earth filled with dinosaurs reaches a distant civilization. Their response begins its return, and the world that finally hears it lies tens of millions of years ahead of us. The entire exchange passes around modern humanity without ever belonging to our time. No better transmitter can solve that delay. Radio waves, laser pulses, and visible light all travel at the same fundamental speed through vacuum. Greater power can make a signal easier to detect, and a narrower beam can concentrate more energy toward the target, but neither makes the information cross the distance faster. A physical spacecraft would take even longer. Anything with mass must travel below the speed of light, so even a probe moving at an extraordinary fraction of light speed would lose a race against the message. Across tens of millions of light years, electromagnetic radiation already follows the fastest route allowed by known physics. That leaves no engineering shortcut that turns an intergalactic exchange into real-time conversation. Technology can improve encoding, sensitivity, direction, and reliability, but the distance itself remains. The only practical way to reduce the delay is to communicate with something closer. This changes the emotional meaning of discovering intelligence far away. A signal from a nearby star could come from a civilization that still exists in a recognizable form. A signal from another galaxy might be more like an archaeological discovery carried by light, proving that intelligence existed while leaving its current fate completely unknown. If the civilization observing Dinosaur Earth transmitted a simple statement saying that it had found our planet, the timeline would connect three different worlds. The Cretaceous Earth that inspired the message is gone. The modern Earth existing while the aliens send it is invisible to them. And the future Earth that receives it has not yet developed the landscapes or civilizations that will hear the signal. Light can connect those moments without making them simultaneous. That is why the phrase, "aliens could be looking at dinosaurs right now," needs to be understood carefully. Dinosaur-era photons can genuinely be arriving at a distant observer now. But the aliens and the dinosaurs do not occupy one shared present. What connects them is information that has spent tens of millions of years crossing space. The alien observers would face the same limitation whenever they looked outward. Their telescopes would also show old stars, old planets, and old galaxies. No civilization gets a perfect live view of the distant universe. Every sky is assembled from light that left different objects at different times. Our own sky works exactly the same way. The farther we look, the older the information becomes. A planet that appears quiet may have developed life since the light left. A world that appears inhabited could have suffered a catastrophe before its signal reached Earth. A technological civilization might be visible in old light, even if its cities have already disappeared. We would have no way to know until newer information arrived. and for sufficiently distant worlds that weight could exceed the entire history of our species. So the communication problem eventually turns back toward our own telescopes. If another civilization can study a version of Earth that is already ancient history here, then every distant world we observe comes with the same warning. The light can be real, precise, and scientifically useful, while the present condition of the source remains completely hidden. And once we accept that a message from Dinosaur Earth could return only to an unimaginably distant future, the same delay turns our own telescopes outward and forces a more unsettling thought. Some of the alien worlds we see tonight may already be gone. Every object in the night sky arrives with a delay. For the moon, that delay is barely more than a second. For the sun, it is a little over 8 minutes. For nearby stars, it becomes years, and across the Milky Way, it can become thousands or tens of thousands of years. The farther we look, the less the word now describes what we are actually seeing. This is usually discussed as a useful feature of astronomy because distant light allows us to study the past. We look at galaxies millions or billions of light years away and receive information from earlier stages of cosmic history. But the same principle becomes more personal when we apply it to planets and possible civilizations, because the object we are studying may have changed dramatically after the light we see began its journey. At 100 light years, the uncertainty grows. A century can alter a civilization enormously. Cities can expand, wars can reshape societies, technologies can become obsolete, and cultures can change in ways that would surprise anyone who saw only the earlier version. If an alien civilization existed on such a planet, the light reaching us tonight would describe a society whose current condition is already 100 years beyond our view. At 1,000 light years, the gap becomes historical. We could be studying a planet as it was around the time of medieval Earth, while its real local present lies 1,000 years ahead of the image in our telescope. A technological civilization detected there might have advanced, declined, moved elsewhere, or disappeared during the interval hidden from us. The farther the distance grows, the more those possibilities become impossible to ignore. A world 10,000 light-years away is being observed through light 10,000 years old. Any city lights, atmospheric pollutants, radioactivity, or artificial structures we somehow detected would belong to a civilization that had 10 millennia to change before our observation even began. We could also see no sign of technology and conclude that the world is quiet, while a civilization has already appeared there after the light we are receiving left. Their cities could already exist, their satellites could already orbit the planet, and their radio signals could already be spreading outward. Yet none of that information would have reached Earth. The opposite possibility is just as important. We might detect a strong technological signature and believe we have found a living civilization, while the society that produced it has already disappeared. The signal remains real. The technology really existed. What changes is the assumption that the source must still exist in the same form today. This is one reason an artificial signal from deep space would answer one question while immediately creating another. It could prove that intelligence and technology existed at the source when the signal was transmitted, but it could not tell us what happened afterward. The farther away the source is, the larger that unknown period becomes. If the signal came from 1,000 light-years away, the civilization had 1,000 years of hidden history after transmission. If it came from 10,000 light-years away, the hidden period becomes 10,000 years. If it came from another galaxy millions of light-years away, the sender belongs to a time so distant that its entire civilization may have risen and vanished before humans appeared. A signal can therefore be both a discovery and an archaeological artifact. It may not be a voice speaking from another world's present. It may be the surviving evidence of a technological era that ended long before Earth was able to hear it. The same uncertainty applies even without a deliberate message. Suppose astronomers identify a distant planet with an atmospheric composition that strongly suggests industry. If such a signature were found, it would tell us that some unusual process existed when the light left, but the atmosphere we measure is still old. If the planet is 5,000 light-years away, its local environment has already had 5,000 years to change. This separation between astronomical stability and civilizational instability is important. Stars can remain recognizable for millions or billions of years, but civilizations may operate on much shorter timescales. A world can therefore look like the same planet in every basic astronomical sense, while the society that once made it interesting has vanished completely. We do not know how long technological civilizations typically survive because we have only one example, and ours is still very young. It is possible that advanced societies remain detectable for millions of years. It is also possible that their technological phases are brief compared with the age of their planets. The difference matters because light travel time can easily exceed the lifetime of a short-lived civilization. Even planets with only biological life can change greatly across long delays. Climate shifts can transform ecosystems. Large impacts can cause extinctions. Volcanism can alter atmospheres. Stars slowly change their output, and planetary systems evolve. A biosignature detected from a sufficiently distant world is evidence for life in the past light reaching us, not a guarantee that the same biosphere survives today. This does not make the observation less valuable. Discovering that life existed elsewhere would still change our understanding of the universe, even if the organisms were already extinct. The difference is that we would need to separate the question, "Did life exist there?" from the question, "Is life there now?" A world 100 million light-years away could, in principle, show evidence of life that existed 100 million years ago. By the time we detect it, the planet may have passed through mass extinctions, climate changes, or entire evolutionary revolutions. We would be studying a biological world whose present may be as different from its observed past as modern Earth is from the Cretaceous. This is not a flaw in our telescopes. Better instruments can reveal more detail in the light that has arrived, but they cannot receive photons that are still in transit. Even an unimaginably advanced civilization would face the same problem. Technology can improve the image, but it cannot remove the travel time. That means no civilization possesses a true live map of the universe. Every cosmic map is assembled from different ages. A star 10 light-years away appears 10 years old. A galaxy 10 million light-years away appears 10 million years old. And more distant objects are seen through increasingly older light. For the search for life, this becomes unsettling, because life can change much faster than many of the astronomical objects that contain it. A planet may remain in orbit for billions of years, while civilizations appear and disappear within tiny fractions of that span. Consider a hypothetical world, 5,000 light-years away. If a technological species emerged there 3,000 years after the light we currently receive left, we would see no sign of it today. Their cities could already exist, and their radio signals could already be traveling outward, yet our telescopes would still show an older, pre-technological planet. Now reverse the timing. Suppose the same civilization existed when the light we see left but disappeared 2,000 years later. We might detect atmospheric pollution or an artificial signal and believe we had found an active society. In the local present of that planet, however, its cities could already be ruins. Both scenarios look identical from Earth until newer information arrives. This uncertainty cannot be removed by interpretation alone. We can estimate probabilities, compare stellar ages, study planetary stability, and model how long signals might persist, but there is always a hidden interval equal to the light travel time. We cannot observe what happened inside that interval, until the information reaches us. The problem grows especially severe when people imagine civilizations in other galaxies. Andromeda is more than 2 million light-years away. Any technological activity we somehow detected there would describe conditions from more than 2 million years ago. A species responsible for that technology could have had time to evolve, spread, transform, or vanish many times over before its signal reached Earth. If a deliberate message arrived from that distance, responding would not begin a conversation with the civilization we detected. Our reply would reach Andromeda more than 2 million years later, and whoever receives it would live millions of years beyond the era of the sender whose original message we heard. At distances comparable to dinosaur Earth, the separation becomes even greater. An alien civilization 66 million light-years away could be visible to us as it existed around the end of the Cretaceous on Earth. If we saw evidence of its technology tonight, the source would already have 66 million years of hidden history. That span is long enough for entire branches of life to evolve and disappear. It is long enough for continents to move across a planet. Whatever civilization produced the observed signal might still exist, but there would be no reason to assume that it does. This does not mean the universe is filled with dead civilizations. We simply do not know. The important point is that distance prevents observation from answering the present tense question directly. That creates a strange possibility when we search the sky for intelligence. We may eventually detect evidence from multiple civilizations, yet every one of those detections could belong to a different period of cosmic history. One signal might be a few decades old, another 10,000 years old, and another millions of years old. We would receive them together in our present, even though the senders never existed at the same time. The night sky could therefore contain a collection of civilizations scattered not only across space, but across history. Some may still exist. Others may have vanished. Some worlds that appear lifeless may already be inhabited, while some that appear inhabited may now be silent. This makes the search for extraterrestrial life less like looking across a dark ocean at distant islands, and more like reading messages written at different dates, with no immediate way to know what happened after each page was sent. The information can be rich and precise, yet every source carries an unseen future. For nearby stars, that future is relatively short. If we found convincing evidence of a civilization 4 light-years away, the hidden interval would be only 4 years. A response could reach the system 4 years later, making an exchange slow but meaningful on human timescales. As the distance grows, the uncertainty grows with it. At 1,000 light-years, we are studying a millennium-old society. At 10,000, we are observing a civilization from before much of human recorded history. At millions of light-years, we are doing archaeology with photons. The same rule that allows hypothetical aliens to see dinosaur Earth therefore turns the entire universe into an archive. We look outward and receive old versions of everything. Any biospheres or civilizations within those systems may have followed histories we cannot yet see. This also changes the emotional meaning of a future discovery. If astronomers announce that a distant planet shows convincing evidence of technology, the statement would need an unspoken date attached to it. The civilization existed when that light left. Whether it exists now would remain unknown. A million-year-old signal could still be the greatest discovery in human history. It would demonstrate that intelligence arose elsewhere and found a way to make itself visible across space. But it might also be the only surviving connection to a society that ended before our species existed. That possibility mirrors the dinosaur Earth exactly. A distant observer can receive a living planet from our ancient past while being unable to know what Earth has become. We can receive an alien civilization's ancient light while being unable to know whether anything remains there now. Both sides are trapped by the same speed limit. And this raises an even deeper problem than distance alone, Because if civilizations can appear and disappear while their light is still traveling, two intelligent species may share the same universe, live relatively close on cosmic scales, and still fail to exist at the right times to ever recognize one another. Distance is easy to picture because it can be drawn on a map. Two stars can be separated by 1,000 light-years, two galaxies by millions, and the empty space between them can be measured. Time is harder to see, yet for communication, it matters just as much. A civilization must not only exist somewhere else, it must also be detectable during the period when another civilization is able to receive its signals. Consider two inhabited planets separated by 1,000 light-years. On one world, a technological species develops radio communication and transmits for 500 years before changing its technology, becoming quiet or disappearing. Its signals continue outward after the transmitters stop, crossing the space between the stars as a moving record of that short technological period. If the second civilization does not develop radio astronomy until long after those signals pass through its system, it may never know they were there. Both civilizations existed in the same galaxy. Both became technological, yet their detectable periods missed each other completely. The reverse can happen just as easily. The second civilization might transmit strongly for centuries, but its signals could reach the first world only after the society there has vanished. To an outside observer, the galaxy contained two intelligent species separated by a modest distance on cosmic scales. But there was never a moment when either could hear the other. This is why the question of alien life cannot be reduced to how many habitable planets exist. A planet can remain suitable for life for billions of years, while a technological civilization may occupy only a tiny fraction of that span. If intelligence appears at different times on different worlds, the periods during which those worlds are capable of detecting one another may overlap only briefly, or not at all. Earth makes the scale easier to understand. Life has existed here for billions of years, complex animals for hundreds of millions, and our own technological era for only a very small part of that history. From a geological point of view, the period in which Earth has produced strong artificial electromagnetic signals has barely begun. If another civilization crossed its own radio age 1 million years ago, on a planet a few thousand light-years away, its transmissions could have passed through the solar system before humans had any equipment capable of recognizing them. The waves would not remain nearby waiting for us to become interested. They would continue outward at light speed and leave no convenient marker saying that a message had once crossed our sky. This creates a form of cosmic bad timing that has nothing to do with intelligence or engineering. A civilization can send a clear signal. Another civilization can eventually arise within range. And still, no contact occurs, because the receiving world becomes capable of listening after the signal has already passed. We do not know how long technological civilizations remain detectable. Humanity gives us only one example, and ours is extremely young. Advanced societies might remain visible for millions of years, or they might become quieter, use technologies we do not know how to detect, move away from planets, or disappear. The exact lifetime is unknown, but the timing problem exists regardless. This also changes the meaning of silence. When a telescope hears nothing from a star, that silence does not prove the system has never contained technology. A civilization could have existed before the light we are receiving was emitted. Another could arise after the era currently visible to us. Our observation samples only one slice of the planet's history. A quiet world can hide both a past and a future. Imagine a planet 1,000 light-years away. Suppose a technological civilization appeared there, 500 years after the light we are receiving tonight left the system. Our telescopes would still show the earlier, pre-technological planet, even though the civilization has already existed locally for centuries. We would not be wrong about the light in front of us. We would simply be early, relative to the information. Now reverse the order. Suppose the civilization flourished 2,000 years before the light we see was emitted and disappeared, 500 years before that light began its journey. The planet could look quiet today, even though an entire technological age had already come and gone there. Both situations produce silence in our instruments, but for opposite reasons. The difficulty is that we usually cannot tell which silence we are observing. We can estimate the age of the star, study the planet's atmosphere, search for radio signals, and look for unusual technological effects, yet a missing signal does not reveal whether intelligence never appeared, has not appeared yet in the light reaching us, or appeared and vanished before the observed period. The universe can therefore contain many intelligent species, without presenting them to one another as neighbors, in the ordinary sense. They may occupy different eras of the same cosmic landscape, connected only by radiation moving between worlds after one side has already changed. A useful way to picture the Milky Way is not only as a disk of stars, but as a history extending through time. Every civilization would occupy a small region in that history, beginning when it becomes detectable, and ending when its detectable phase changes or disappears. Contact becomes possible only when signals from one region reach another civilization during a period when someone is able to notice. Two planets can be physically close and still miss that intersection. One civilization's signals may pass through the second system too early, while the other's transmissions arrive too late. Nothing blocks the waves. The problem is only that the listeners are absent at the wrong moments. Earth shows how easy such an interval would be to miss. An observer receiving our planet from 10,000 years ago would see humans and growing settlements, but none of the global technological systems that define the modern world. An observer receiving Earth from 1,000 years ago would see organized civilizations, but still no radio transmissions, satellites, or industrial atmosphere like today's. Only observers close enough to receive very recent Earth can begin to see the technological era we recognize. From farther away, humanity exists, but technology does not. Farther still, humans disappear, continue outward, and eventually the arriving Earth belongs to the age of dinosaurs. The same could be true of worlds we are observing tonight. There may be planets whose ancient animal life is visible to us, while intelligent descendants already exist locally. There may be planets showing technological civilizations that disappeared thousands of years ago. There may be worlds that look lifeless because we are receiving light from before biology took hold. Without newer information, these possibilities can hide behind the same distant point. This is why a single confirmed detection of technology would be so important, even if the signal were ancient. It would prove that intelligence arose independently elsewhere. But the discovery might also make the universe feel more distant, because the signal could be thousands or millions of years old, and tell us nothing certain about whether anyone remains. That would be a different kind of loneliness from believing we are alone. It would mean the universe can produce minds and civilizations, yet the scale of space and time still prevents them from sharing a common present. Two species do not need to be separated by impossible physics to miss each other. They only need to become detectable at different moments. This possibility may help explain why a quiet sky is difficult to interpret. Silence could come from great distance, weak signals, different technologies, short detectable lifetimes, or simple timing. None of those possibilities proves that civilizations are common, but they show why silence cannot be translated directly into emptiness. The same timing problem applies even before technology. Two rich biospheres can flourish at different times around different stars and never overlap. One planet may develop complex life, while another is still sterile, then suffer an extinction before the second reaches the same stage. Planetary histories do not move together. Stars are born at different times, planets form at different times, and stable environments begin and end at different times. Evolution proceeds through events that do not follow one universal schedule. There is no reason to expect intelligent species across the galaxy to appear during the same narrow interval simply because the universe is old enough for them to exist. Earth reached technological civilization very late in its own history. Another world could reach that stage much earlier or much later. A civilization around an older star might have appeared hundreds of millions of years before humans, while one around a younger system may not emerge until long after our own technological era has ended. When these differences are combined with light travel time, the galaxy begins to look less like a room full of civilizations waiting to speak, and more like a vast history in which brief lights turn on and off at different places. Some signals cross another inhabited system at the right moment. Others pass through before anyone is listening, or arrive after the receivers have disappeared. There may never be a single moment when all intelligent life can see one another. This returns us to the distant observers receiving Dinosaur Earth. They could be intelligent today while the Earth visible to them contains no humans at all. Their civilization and ours could both exist in the universe at what each considers its present. Yet the information connecting us is so delayed that neither has access to the other's present condition. They see our deep past. If their world were equally distant from us, we would see theirs. If their civilization became detectable only recently, the light showing it may not reach Earth for tens of millions of years. If humanity's technological era ends before then, the signal could arrive to a planet where no one remains capable of recognizing it. The two civilizations would have overlapped in cosmic time and still missed each other completely. That possibility is more subtle than simple distance, because nothing has to block the signal. No wall exists between the worlds. The photons travel normally. Physics works exactly as expected. The failure comes only from the fact that sender, receiver, and information do not arrive in the right order. For any civilization hoping to find another, nearby stars are therefore especially valuable. Their planets are not only brighter and easier to study, their information is more recent. A signal from a world 10 light-years away describes a past only 10 years removed from us, while a signal from a million light-years away belongs to an age no observer can update for another million years. Even nearby contact would be slow, but it could still belong to recognizable history. Across millions of light-years, the hidden interval becomes the main story. And that brings us back to the image that started this journey. Somewhere far away, an observer could be receiving the light of a green and blue Earth from the age of dinosaurs, unaware that those animals vanished, unaware that mammals later changed the planet, and unaware that a technological species would eventually appear tens of millions of years beyond the world. In its telescope, the observer's picture would not be false. It would simply be old. Our picture of the distant universe carries the same limitation, and every civilization that ever looks outward is trapped inside it. No one sees the cosmos all at once. Everyone receives pieces of history at the speed light allows. And once that is understood, the image of aliens watching Dinosaur Earth becomes more than a strange possibility, because it reveals the deeper truth that every civilization looking across the universe is surrounded by worlds whose present it may never live long enough to see. Somewhere tens of millions of light-years from us, the photons leaving Earth near the end of the dinosaur age are arriving at new locations right now. Most will pass through empty space without ever entering a telescope. Some may cross galaxies without touching anything at all. A tiny fraction could, in principle, fall onto the instruments of a civilization capable of noticing that one faint star among billions has a small rocky planet moving around it. If such observers exist, the Earth available to them is not the world beneath our feet. They do not receive our cities, our satellites, our radio towers, or the changing lights of the modern night side. The information reaching them belongs to an older planet, one with different continents, different coastlines, different climates, and a biosphere dominated by organisms that disappeared long before our species appeared. That does not mean they would see a Tyrannosaurus walking through a valley as though they were watching a film. At such an enormous distance, Earth would be extremely difficult to isolate from the Sun, and an individual animal would be unimaginably too small to resolve with anything resembling the telescopes we know how to build. The scientifically meaningful version of the idea is quieter and more interesting. They could be receiving light that left while dinosaurs were alive. If their technology were extraordinary, they might detect Earth as a point beside the Sun. They might measure its orbit, estimate its temperature, and study how its brightness changed as the planet rotated. They could search its spectrum for water vapor, carbon dioxide, oxygen, ozone, methane, and other gases, slowly building a picture of a world whose atmosphere and surface behave in ways that suggest activity. The planet might reveal oceans without showing a shoreline. It might reveal weather without showing a cloud. It might reveal a biosphere without showing a single organism. If that happens, we may find ourselves in the same position as the hypothetical observers studying dinosaur Earth. We could know that a distant world is alive while having almost no idea what its life looks like. We might infer oceans and an atmosphere, perhaps even a global biosphere, yet remain unable to tell whether the surface contains microbes, forests, animals, or something unlike any organism on Earth. And whatever we discover would already be old. A planet 50 light-years away would be seen 50 years in the past. A planet 500 light-years away would appear 5 centuries old. Across the Milky Way, a possible civilization could be observed tens of thousands of years behind its own local present. Beyond the galaxy, the delay becomes large enough to separate entire evolutionary eras. The night sky therefore contains no single cosmic present waiting to be photographed. Every direction carries information from a different time, determined by the distance the light has crossed before reaching us. Nearby objects arrive almost current, while distant galaxies appear as they were millions or billions of years ago. This is not an illusion created by weak instruments. It is how information moves through the universe. A larger telescope can gather more photons and reveal more detail, but it cannot show an event whose light has not reached us. No increase in magnification can display a planet's future, and no detector can recover a modern Earth from 66 million light-years away when the photons showing modern Earth are still traveling through the intervening space. Their knowledge could be extremely accurate and extremely old. That creates one of the strangest features of cosmic observation. The farther away something is, the more carefully we must separate what we know about its observed state from what we assume about its present state. A star may still be shining when we see it, but it may have changed since the light departed. A planet may show signs of life that no longer exists. A world that appears empty may already contain a civilization whose signals have not reached us. There can be no telescope pointed at the entire universe that shows everything as it is at one shared moment. For Earth, the effect can be imagined as a history traveling outward. Recent light remains relatively close to the solar system. Farther away are photons from earlier human history. Beyond those lie versions of Earth from before civilization, before our species, before many familiar ecosystems, and eventually, from eras when the planet itself looked profoundly different. Somewhere closer than the dinosaur-like distance, an observer could receive an Earth where early mammals are spreading through new ecosystems. Closer still, the latest light could belong to early humans. At smaller distances, agriculture and cities begin to appear, followed much later by industry and technology. Only within the very small region reached by recent human signals can an observer even begin to receive evidence that Earth has become a technological world. That region is tiny compared with the scale reached by ancient natural light. For billions of years, Earth reflected sunlight and emitted radiation while life changed the atmosphere and surface. Our radio age, by comparison, occupies little more than a moment. So a civilization receiving Cretaceous Earth would not merely fail to see modern humanity. Humanity has not entered its observable history yet. From their perspective, the future of Earth remains sealed inside photons that have not arrived. The extinction of the non-avian dinosaurs, the rise of mammals, the appearance of humans, and the construction of our technological world all lie ahead in the stream of information, even though every one of those events is already past for us. If those observers could survive and continue watching for millions of years, later versions of Earth would slowly arrive in the correct order. They might see broad signs of environmental disruption around the end of the Cretaceous, followed by recovery, changing climates, and new ecosystems. Much later, the planet would begin showing the subtle effects of human activity. But there would be no way to skip ahead. That inability to fast forward is what turns cosmic distance into cosmic separation in time. The observer cannot ask what Earth became and immediately look up the answer. Nature delivers the answer at one speed and across 66 million light-years. That means waiting 66 million years slice of history to catch up. The message could still matter. It could prove that intelligence arose somewhere else. It could carry mathematics, images, language, or a description of another world. But it would not create a normal conversation between contemporaries. It would connect different eras. Civilizations can miss one another without ever being separated by anything more exotic than distance and timing. A species could transmit for thousands of years while its signals move outward, then vanish. Another civilization could develop within range after those signals already passed. Both would have existed in the same galaxy, and both might have searched for life, yet neither would ever know the other had been there. A distant world could also appear completely lifeless because we are seeing it before life emerged. The opposite could happen as well. We might detect a rich biosphere in old light, while the planet's local present has become sterile. Every observation carries an invisible question about what happened after the photons left. The farther away the object is, the larger that hidden interval becomes. At a nearby star, it may be only a few years. Across the Milky Way, it can be tens of thousands. Across the distance required to see dinosaur Earth today, it becomes tens of millions of years, enough for entire ecosystems to vanish and new ones to replace them. Relativity makes the idea of a single universal present even more subtle. But we do not need advanced equations to understand the practical result. Information cannot reach us faster than light. That alone is enough to guarantee that distance and delay are inseparable. When we look at the moon, the delay is too small to feel. When we look at the sun, we see it a little more than 8 minutes ago. When we look at nearby stars, we see years into the past. When we look beyond our galaxy, we are watching events that happened before our own species existed. The farther our telescopes reach, the deeper the universe becomes in time. Dinosaur Earth would be the same. If an observer receives those photons, it is genuinely receiving information from Earth. The atmosphere was real, the clouds were real, the oceans and continents were real. The organisms influencing the planet's biosphere were alive when that light began traveling. What is missing is the update. This may be the clearest way to understand the entire idea. The universe does not show every observer the same live version of every world. It sends updates at the speed of light, and the farther away the observer is, the longer the update takes to arrive. A civilization 100 light-years away has not yet received everything that has happened on Earth during the last century. A civilization 10,000 light-years away is missing 10,000 years of our history. One tens of millions of light-years away is missing enough time for the entire human story to disappear from its view. Meanwhile, we are missing equally large pieces of their histories. If intelligent life exists in another galaxy, its modern state could be forever inaccessible to us in practice. We may receive evidence that it once existed, perhaps even detailed evidence, while knowing that the world producing it has already lived through millions of additional years. The discovery would still answer one of humanity's oldest questions, but it might do so in a way very different from the stories we usually imagine. We could learn that we are not alone, without ever speaking to anyone who shares our time. We could find a civilization only as history, and somewhere else, another civilization could find us the same way. Perhaps the most unusual part of the dinosaur Earth idea is therefore not the dinosaurs themselves. It is the realization that every civilization becomes an ancient object when seen from far enough away. Modern Earth is modern only here. Give its light enough time to travel, and today's world becomes another fossilized moment, moving through the universe. The photons leaving Earth tonight will cross 1 light year after 1 year, 1,000 light years after 1,000 years, and millions of light years after millions of years. They will carry a faint record of our clouds, atmosphere, oceans, and whatever technological changes are large enough to affect the outgoing signal. By the time those photons reach distant galaxies, Earth will have continued changing without them. Some may arrive at worlds where no observer exists. Some may pass through empty space forever. And perhaps, an unimaginably small fraction will one day enter an instrument built by another intelligence, which will look toward the Milky Way and begin asking what kind of world produced them. If that happens, those observers will not be seeing us as we are when they ask the question. They will be seeing whatever version of Earth had enough time to reach them. For some, that could be humanity. For others, it could be an empty pre-human landscape. And at roughly the right distance, the newest Earth they can receive may still belong to a world of ancient oceans, unfamiliar continents, thick forests, and dinosaurs moving through ecosystems that disappeared tens of millions of years before any human ever looked up and wondered whether someone else might be watching. So the strange answer is yes. Somewhere far enough away, the light of dinosaur Earth can be arriving right now, and an observer there could in principle be studying that ancient version of our planet. Even though seeing an actual dinosaur would require observational abilities far beyond anything we know how to build. But the deeper truth is larger than the title. The dinosaurs are only one example of what light does to every world in the universe. It turns distance into history, separates civilizations from one another's present, and ensures that whenever we look far enough into space, we are never simply looking somewhere else. We are looking backward in time. And somewhere in the darkness, the same is true for anyone looking back at us. Good night.